good of business, let me start by saying that as far as I can tell, thankfully, everybody has now logged into WebAssign. So I don't need to talk to anyone and say, hey, Jimmy, come on, let's get a move on. I've also fixed the dates at which the homeworks are due, so that should be good now. And they are due, as I kind of promised, midnight Sunday. Now, what's not in WebAssign yet is online test 1, but as I said before, that won't appear until Friday. So that's part of this week's assignments, right? There are 2 sections that we need to get completed today, but we've got just slightly under 2.5 hours to do that. So let me get right into it. Give you a kind of overview, hopefully what we'll get covered. Going to look at section 12.2, and 12.2 is basically the intro to vectors. We're going to be doing these and some other topics. And then in section 12.3, we're going to do, still on vectors, we're going to look at dot products. But everything is really concerned with 3 dimensions. So if you've ever done any vectors at all, the chances are, if you have done vectors, that it's more than likely you did 2-dimensional vectors. Right? So they're only an X component and a Y component. All we're going to do in Calc 3 is extend that to the 3-dimensional world. So imagine this pen is a vector. It has a start and the tip is a finish. And when we draw vectors, we might have this point here, we'll call it A, and this point here is called B. And if you join A to B, that's a vector. A vector is essentially a movement in space. In this case, pretend that's 3D space, right? And vectors have a direction from A to B, right? And they have a magnitude, right? Some vectors are much longer than others. Vectors are very often used to represent force. So if you have a point in space, you might have 3 things pulling it. Can you imagine you've got a ship and there's 3 tugboats pulling it in different ways, and one tugboat's quite strong and the other 2 are quite weak? We can model that using vectors and come up with a resultant force. So vectors can be added together, subtracted and multiplied, and lots of other things. So let's talk about notation. A vector can be written down like that. That's the most common way, and that's the way I'm going to write them. A to B, like that. You might have seen a vector written with a funny little hat above it. Some people use that notation, but I won't. I just want to use one notation rather than keep mixing and matching. That is also a notation to represent the vector AB. Sometimes vectors are written like that, a little V, and that's representing the same vector. And sometimes vectors are written V with a little hat above it, but that's pretty rare. So the most common notation is going to be AB with an arrow above it, or the vector V with an arrow above it. And if you see these are vectors. However, if you look at a textbook, and they're a little bit different, you will see that notation in textbooks representing the vector joining the point A to B. But you won't see that notation. What you see in a textbook, and it's sometimes you have to look really carefully, they do the V in bold. Right. So if you're looking at a homework question and you see V like that, you know that V is a vector, not a variable, right? And so a vector has a direction and it has a magnitude. So that's kind of what is a vector. Well, it's a directed line segment. It's a movement in space from a point A to point B. Now we're going to look at, well, how do you calculate or how do you represent a vector? Well, can you imagine this guy has coordinates 1, 3, 5, and let's have this guy coordinates 7, 4, 7. So you can imagine, 2D space. If you want to find the components of the vector AB, that means the numbers that represent it. You'll see it very often written like this. Do you see these funny little greater than and less than symbols, they're nothing to do with greater than and less than. They are actually used as if they were brackets, right? And you take that guy and subtract that. So you go 7 take away 1. You go 4 take away 3. And you go 7 take away 5. And so if I wanted to go from A to B, I would move 6 units in the X direction, 1 unit in the Y direction, and 2 units in the Z direction. And this number is called the X component of the vector. This number will be called the Y component of the vector. And this guy here is, not surprisingly, the Z component. So normally when you tell someone a vector in 3D space, what you really tell them is these 3 numbers. And these represent how you would start at some arbitrary point A and finish up here at B. And so these 3 numbers represent our vector AB. Does that look vaguely familiar to anybody who has been doing vectors in science and physics, for instance? Does that look familiar? When you did your physics version of vectors, did you only do 2-dimensional vectors, which meant you had 2 numbers? Or did you see 3? Just curious. Can you remember?
I have to rename your name, Eric.
I didn't catch that, Natalie? I think it was Natalie who was talking.
Okay. I will use your computer.
No, she was talking to someone else. Okay, that's it. 3 components, X, Y, and Z. So let's generalize it. Suppose I have a point in 3D space with coordinates x1, y1, z1, and I have another point B, and its coordinates are x2, y2, z2. If I want to find the vector AB, the formula for it is x2 take away x1, comma, y2 take away y1, comma, z2 take away z1. And that's essentially the general formula for finding the vector from A to B. And one of the things you've got to notice is, do you notice it's the second guy goes first, right? So these are the numbers that go first, and these are the numbers you subtract. So you might get a question that looks something like this. P is the vector 0, 2, 4. Sorry, P is the point 0, 2, 4. Q is the point -3, 1, 5. And you're being asked to find the vector PQ. The way I typically do these is I just say to myself, second, take away the first. So -3, take away 0, right? 1, take away 2. And finally, 5, take away 4. And in this case, -3, -1, 1. And we now have our vector PQ. So if you want to find a vector joining 2 points together and you know the coordinates of them, that's essentially how it would work. So an example of that from the homework would be a question like question 5. In question 5, the starting point A has coordinates 3, 0, -2. And the end point will have coordinates 3, 3, 2. And we're being asked to find the vector AB. So, second, take away the first. 3, take away 3. Second, take away the first. 3, take away 0. Second, take away the first. 2, take away -2. That guy gets you 0. 3 take away nothing gets you 3. And 2 add 2 gets you 4. And there would be your answer. The vector joining A to B, you'd start at any point you like, but you could start at A if you like. Move 0 in the X direction, move 3 in the Y direction, and then move up 4 in the Z direction. And from wherever your starting point is, join it to your end point, and that would represent, a vector like that in 3D. Now I'm going to nip over to the homework and show you how you would write that down in WebAssign. So you should be looking at question 5 right now. If you click on that, you see the little calc pad appears. Choose the one called vectors. And that funny little guy there gives you the brackets that I was using. And then you simply just type in 0, 3, 4. I think it'll fill in the other guy you did. And that's you. What you don't do is on your keyboard, use the less than symbol and type in 0, 3, 4 and finish with that. Now, doesn't that superficially look like it's the way I just wrote it? If you type that into WebAssign, it'll just say, I don't know what you mean, and you're wrong. So remember, anything to do vectors, you're probably going to use vector button and write the guy down. And do you see the funny little guy with the hat above it? If you wanted to write down, let's suppose the answer to a question was the vector AB, right? Just for argument's sake, click that guy, and then you can just put in AB. So that's how you would write AB down, right? A vector AB. And you might have a question where that's what you do. Any questions so far? So if I gave you the coordinates of 2 points in 3D space, are you comfortable you'd be able to find the vector joining A to B? Okay, let's move on then. Next thing we're going to look at, quite a lot of notes today. Next thing we're going to look at is some special vectors. There is a vector called the 0 vector.
1 second, can I look at 5 again? Sorry, I was a little late because I
No
got
problem.
blocked from
I'll put
the
it there
Zoom.
for you. Right, so special vectors now. These are vectors in 3D space that have been found to be useful. And because they're found to be useful, they're given their own name. Like pi is a useful number, so it gets pi. The 0 vector is 0 with a little arrow above it. Unless it's a textbook, in which case it will look like a 0 but in bold. Now, in the 3D world, the 0 vector is 0, 0, 0. If you were going to create a 3-dimensional vector that was a 0 vector, would you agree 0, 0, 0 is kind of intuitive? That's what you probably would call it, right? Now, it's really weird, this vector, because if I said to you, I'd like you to draw that vector, right? Then imagine we're in 3D space. You would start anywhere you like, because vectors don't really have a starting point. You can pick anywhere to start. Your instructions are now, from that starting point, go 0 in the X direction, so don't move. Then go 0 in the Y direction, which really means don't move. And then go 0 in the Z direction, which means don't move. Isn't a point in space then, any point in space, an example of the 0 vector? Now, why are 0 vectors helpful? Sometimes you have a situation where, can you imagine you've got 3 vectors pulling in different directions, some are stronger, longer means stronger, and you want to find a single vector that would balance it, right? Then the way you would do that in physics is you would find the missing 4th vector so that when you add all 4 of them together, they equal the 0 vector, right? It's a balance of forces question. You may have had to do some of those kinds of questions. How much force would I need to balance this stress on an object, right? So I don't want it to fall, the pole to fall over. So what would I have to pull against it to keep it vertical? Zero vectors are useful. Now, the next group of special vectors, and there's only 3 more of them, and they belong together, are called the basis vectors. And there are 3 of them. And they are I, J, that's right, I said J, and K. And the basis vectors are the basis or the building blocks of all 3-dimensional vectors. So for instance, I is 1 in the X direction and no movement in the other 2. The vector J is 1 unit movement in the Y direction and nothing else. And K is 1 unit in the Z direction and no movement in the other 2. Now, these are the basis vectors, right? They're called I, J, and K. And if you want to take any vector, let's suppose I have a vector that I've already calculated, and it was 1, 3, -2. Right? I could tell you the vector using this notation, right? I could also tell you that it is 1i plus 3j take away 2k. Would you agree that this is equivalent to that? I, J, K vectors. They are called the basis vectors. Sometimes in WebAssign, you'll do a calculation with vectors, and they want the answer to be written like that. And sometimes you'll do calculations in vectors, and they want the answer to be written like that. Right? So they're equivalent, right? These are the same thing, right? The same vector, just 2 different ways of doing it, right? This is the IJK notation. This is component notation. Any questions about those? You comfortable? You might have seen them. Right. So 0 vector is special, and the 3 basis vectors I, J, and K. We're not going to do this, but just for completeness sake, couldn't I do 4th dimensional vectors? Wouldn't it be not that difficult to tell you what a 4th dimensional vector would look like, even if I couldn't draw it? Right? Wouldn't it just have 4 numbers instead of 3? Right? You can have 10-dimensional vectors if you really found a reason to do it. There's no limit to them. But we're only going to stick to 3. So, next thing in my little list is, how do you find the magnitude of a vector? So, suppose I have a vector V, and it's 1, 3, -4. And I want to know the magnitude of that vector. I want you to just pretend that this line is the 3D picture, right? It's a pen, it's sticking out the paper. That's the guy. When you talk about the magnitude of a vector, all you really mean is the length of it, right? How long is it? And there's some notation that we use. The one that we're going to use is that one. So it's the vector, and then like the absolute value, you see the 2 vertical lines next to it? That means the magnitude of the vector V. You can also see it written like that. It depends on what information, right? That's still a vector, so that would mean the magnitude of the vector AB. This would be the magnitude of the vector V. In fact, if I tell you that's A and that's B, don't they match up really nicely? Does anybody remember, those who've dealt with vectors, the formula for calculating the magnitude of a vector? Anyone remember that? None comes to mind? Okay. Let's show you it then. The magnitude of a vector is the square root of its components squared and added. So 1 squared, 3 squared, -4 squared. So getting the magnitude of a vector is actually quite straightforward. Don't you take its components, square them and add them like this. So in this case, that's going to be the square root of 1 plus 9 plus 16. And that's going to be, in this case, the square root of 26. Are we good? Right. Question, Colin.
No, I realized I was muted. I was going to say, just hold on 1 second. I'm just finishing.
No problem. So we have got a method now for finding the magnitude of a vector. Simply just take the x, the y, and the z components, square them and add them inside the square root. If the square root can be made simpler, you should. If it's no good, you leave it alone. So if it was the square root of 25, I'd say the magnitude was 5. If the magnitude was square root of 20, I'd turn it into 2 root 5, for instance. It's just good math to simplify when you can.
So what are the hash marks after the AB mean?
Is it these two vertical lines?
Oh,
Sure.
no, that's the one after the equal sign. You got like,
Oh, these little dashes?
they look like quotation marks.
They are. I don't know. I've used this for years. I guess it's maybe not an American thing. It just means it's the same words as the words above, so I don't have to write them.
Oh, okay.
Do you use it in America?
I've
Please
never
tell me
seen
you do.
that being used, no.
Well, some do, some don't. It's just convenient, isn't it? You don't want to keep writing the same thing if it's going to be the same words as the one above. So that's all those
Okay.
little marks mean.
All right.
Right, let's move and try that again. Suppose I gave you the coordinates of 2 points. And the first question would probably be, find the vector AB. And the second question would probably be, find its magnitude. So let's see how we would tackle each of these. Right. To get the vector AB, we've already done questions like that. Second, take away the first. 5 take away 3. 1 take away 0. And 3 take away -3. And that becomes 2, 1, 6. So the vector joining A to B would be 2, 1, 6. Now the magnitude of that vector will simply just be the square root of each of its components squared and added. That's 4, add 1, add 36. And I believe that's square root of 41. And I'm doing a quick check in my head. Nope, I can't simplify it, so that's the answer. Right, can't make it look better. Are you comfortable now that if I gave you the coordinates of 2 points, you could find the vector AB? And that if I gave you a vector, you could find its magnitude? Feel comfortable with those two? Okay. Which means we can now move on to how to find what are called unit vectors.
I got a question real quick. if you don't
Yes.
mind.
No problem.
So the arrow over the AB, right?
Yes.
That represents being a vector.
Yes.
Do you always keep it even though you're just finding a magnitude and not a direction? Because you already found the direction by finding vector AB, right? And then,
Are you saying when I write the magnitude, do I keep the arrow above it and I write this down? Is that what you're
yeah,
asking?
is
Yes,
that-
you do. That's just convention. Right. I don't know if you've got a physics professor who kind of just says AB. That could happen. I think that's slightly loose notation. It's not wrong, I guess, but I like being consistent, so I always use vectors have arrows. Whether I find the magnitude of them or not, I still keep the arrows as part of the way you write it. The minute you put the vertical lines down either side, that now means magnitude. So I can tell just from the notation which it is. Now let's look at what a unit vector is. I want you to imagine that this here is just a vector of no particular length. Then a unit vector is a vector, and let me actually draw it, look like that, and I'm going to call it U. A unit vector is a vector the same direction as V, but whose magnitude is 1.
So, quick question on the
Yes.
the smaller vector.
Yes.
What is that writing next to it on the orange one?
This one
Yeah.
here,
Yeah.
it's a very badly drawn little arrow.
And is that a U underneath the little arrow?
Yes, it's a U.
Okay, thank you.
Try that again. Yeah, is that a little bit better? It's a U. So a unit vector is a vector the same direction as V, but just 1 unit long. And unit vectors can sometimes be interesting and useful things to calculate, because in a sense, the unit vector is telling you the direction of the thing. It's saying, look, it's going that way. And you are not interested maybe in some situations how big it's going that way. You just want to know it's going that way. So unit vectors can be a way of comparing like with like. Now, how do we calculate a unit vector? Well, it has a formula. The unit vector is 1 over the magnitude of V. So that's a number, right? It's like 1/5, 1/3, 1/2, right? Of the vector V. So what we're going to do is we're going to find the magnitude of that vector. And if it's 10, then this guy is going to be 1/10 that guy. Now, if that's 10, 1/10 of it give you a vector that's 1 unit long, right? You've reduced everything by a factor of 10. You'll have converted it. So imagine I give you a vector 3, 4, -12, and I ask you to find its unit vector. Well, the first step is you have to find the magnitude of the vector V. And we can do that. It's the components 3 squared, add 4 squared, add -12 squared. That's how you find the magnitude of vector V. In this case, that's 9, add 16, add 144. And that ends up being 169, which comes out as a nice number because I made it come out as a nice number. The length or magnitude of this vector is 13 units long. So can you imagine from here to here is 13 units long. Now, if you want to find a unit vector, all you need to do is find this guy here. So the unit vector is going to be 1/13 whatever vector V is. Now, if you want to find 1/13 of that vector, it's actually not that hard. 1/13 of each component. So it's 3/13, 4/13, and -12/13. And there's a property of vectors that says if you take any vector at all, and you multiply it by a number, whether that number is a fraction or not, the second vector, this one here, is bound to be parallel to the first one. The only difference is that its magnitude will be reflected by this value here. Does that make sense that if you wanted to get a vector, you just need to find out how long the big guy is, and then do 1 over that number, and you can shrink it down to your unit size? And you can check that. I bet you if you found the magnitude of this vector, it would be 1. I guarantee it. Right? So if you squared this, squared that, and added, you'd get exactly 1. Check it if you don't, please. And by the way, that's step 2 there. Okay. So to calculate a unit vector, we find the magnitude of the original vector, and then we divide by that value. I'm going to look for a homework question like that, just to kind of give you an idea of what they look like. This is a version of question 11. In this case, you're given a vector, and it's given in terms of I, j, and k. And you're being asked to find a unit vector of this guy. Now, they don't give it a name, but I'm going to call it V because I like to call vectors something. So V is that guy. Second thing I'm going to do that most people don't bother, but for me it's easier. There we go. That says 2k. Is I like to turn it into its component form. Something psychologically just makes it easier in my brain to see a vector written this way rather than I, j, k. Just looks nicer. Now, I find the magnitude of V, which is that guy squared, that guy squared, and that guy squared, which is the square root of 9, which comes out as a nice number. The magnitude of this vector is exactly 3 units, square root of 9. The unit vector, well, in this case, the unit vector will be 1 over the magnitude of V times the vector V. And that's going to be 1/3 the vector V. And that becomes 2/3, negative 1/3, 2/3. Whenever you take a vector and multiply it by something, whether it's a fraction like 1/3 or a whole number like 5, and we call that process a scalar multiplication. Scale is just an old-fashioned name for number, right? So scalar multiplication, if you ever see a term, and there is your unit vector. It will be parallel to that vector, but this guy will be 1 unit long rather than the original, which would be much bigger. So that might be V, and this would be what U would look like. Right? Parallel to it, but 1 unit long. Any questions about unit vectors? We good? Someone tells you a vector, you feel comfortable you could find the unit vector. As long as things are numbers, right? Which is what you'd expect. So the next version is a different kind of puzzle. Suppose I have a vector U, U's a bad choice. Suppose I have a vector V, and it's 3, 1, 2, right? Now we're going to make life difficult. I want a vector parallel to that one, but I want a vector not only parallel to it, I want it to be a certain length. So it has to be parallel to V, and it needs to have a magnitude of 10. So if you can imagine this is V, and it has whatever the magnitude is, I want this other guy, I'm going to call him W, to be parallel to it, but I don't want it to be 1 unit long. If I did that, I would just say find the unit vector. I want this second vector to be big. I want it to be 10 units long instead of whatever that one is. So we have to figure out a strategy for being able to solve that puzzle. How do you get a vector that's parallel to this one, but 10 units long instead of whatever that happens to be? So here are the steps to do that type of question. Step 1, find the magnitude of vector v. So we're going to approach it as if we were going to get a unit vector, right? So I'm going to start the same way that we did the unit vector question. So I'm going to find the magnitude. And the magnitude of this vector v is 3 squared, which is 9, plus 1 squared, plus 2 squared. So it ends up a rather ugly square root of 14. Are we cool with that? Magnitude of vector. Now, step 2 is I'm going to find the unit vector of this fella. Well, we know how to get the unit vector. It's 1 over the magnitude of the vector times this fella. So the unit vector is 3 over root 14, 1 over root 14, 2 over root 14. And you should be thinking right now, but that's just what we did in all the other questions. What's different? Well, that's not our finish. This is the sneaky part. I don't want to know a vector that's 1 unit long parallel to v. That's what this is. I want to know a vector that's 10 units long and parallel to v. And I'm calling that vector w, right? How do you think I can use this vector to find the one that's 10 units long? And don't make it hard for yourself.
Multiply by 10, each one.
So 10 times the unit vector, right? So you times each one by 10, and it's not pretty, but it's correct. Is there a logic to that process? Does it make sense how you would approach the puzzle? I want a vector parallel to v, but I don't want it 1 unit long, because that's what this guy is. I want it to be 10 units long, or 5 units long, or 6, whatever number you decide to ask someone to do. Still find the unit vector, but add an extra step. Are we cool with it? Now, an example of that question would be number 13. And question 13, we're given a vector 6 to -3, which I'm going to call v, although they don't call it nothing. And we're wanting a vector that's parallel to this one, but we want it to be 5 units long. So here is a vector. We want a vector parallel to this one, but to be 5 units long. So step 1 would be to find the magnitude of this vector, which is that guy squared, plus that guy squared, plus that guy squared, which ends up being the square root of 49, which is a very nice number, right? It's exactly 7. And then in step 2, I'm going to calculate the unit vector, which is 1/7, because that's 7, of this guy. And if you multiply each of these by 1/7, the unit vector is 6/7, 2/7, -3/7. Is it looking good? Now, I know we've only seen one, but I hope it's intuitive what the next step is going to be. And to find this vector that they're talking about, I'm going to call it W. It's going to be 5 units long. Well, don't I just multiply the unit vector by 5 then? So it's going to be 5 unit vectors worth, which is 5 times this guy. And you end up with 37ths, 10/7, -15. Oops, that's just sevens. And that's us. So if I give you a vector and say I want a unit vector, you feel comfortable about calculating a unit vector. If I say, here's a vector, I want somebody parallel to it, but 10 units long or 5 units long. I'm comfortable about how we would do that.
Is it always going to be 5 units or 10 units, or can it be anything?
Oh, it could be anything. I just picked those numbers. The ones that they've got in question 13 is 5. The other version of that, they want it to be length 6. They could want it to be length 3, 43, or pick a number.
Okay.
And that's all you need to know, isn't it? If you want it 5 units long, 5 times a unit vector. If you want it 6 units long, isn't it going to be 6 times the unit vector? So this number depends on what you were asked to find up here. Actually, now I'm thinking about it, couldn't you get one that's half a unit long?
Why
Couldn't you
not?
just do,
Why not a quarter?
why not a quarter? Exactly. You could make anything you like. Because once you've got a unit vector as like a building block, can't you generate any vector length you like that's parallel to V?
Will there ever be times where we're not given the units?
What do you mean by not given the units? Not given V?
Yeah.
And I can't think of how you could answer the question there. So
Okay.
I would say no, I don't see that being a realistic
Or
situation.
rather, no. Where you're not given the magnitude.
If you're not given the magnitude, it's similar kind of thing, then you've nothing to do.
Okay.
I mean,
just
they
curious.
could make the magnitude vague. They wanted it to be A units long.
Yeah.
case-
That's what I meant.
Yeah. Then you would just do A times U, and this would become 6/7 A, 2/7 A, -3/7 A. So even in that case, you could really still do something. Now, the last part of this section
Oh,
is,
One thing.
sorry, the second last part, there's something else after this that we want to do, is the algebra of vectors.
Oh, 1 sec.
Yes.
So what do you do with the brackets? Like, why do you have the bracket for V, X, and not for U or W?
Why do I have the brackets for?
Like, the absolute value sign.
Right, this
No,
is
it's not
this is for the magnitude of the vector V, which is 7. These are
Okay.
vectors. These are not magnitudes. These are calculating the values of vectors, so they don't have it.
Oh, it's not magnitude?
No, these two are not magnitudes. This
Okay.
is what the vector U is, and this is what the vector V is. If you're looking for a magnitude, when you're finished, there should be a number there, like 2 or 7 or 4. When you do vectors, shouldn't there be a vector at the end of the calculation, as there are here and here?
Okay.
So U equals is a vector, W equals is a vector. That's a magnitude of V, so the answer is a number.
Okay.
Right. So we're going to do the algebra of vectors. And algebra is basically, how do you work with vectors? Can you add them? Can you subtract them? Can you multiply them? What can you do with vectors? Well, let's show you a little list of what you can do. You can add 2 vectors. You can subtract 2 vectors. Yeah, I'm using those little funny dotted quote marks again. Right. Third thing is you can multiply a vector by what they call a scalar. In the language of vectors, scalar just means a single number, like 5 is a scalar, right? 3 is a scalar, a half is a scalar, -2 is a scalar, right? So when you multiply a vector by a scalar, they're talking about things that we've actually done, like 2 times this vector, 4 times that vector. That would be multiplying a vector by a scalar. Right? So let's have some vectors and show you what the algebra looks like. So there's my vector u, and this is going to be my vector v, and this is going to be my vector w. So I have 3 vectors, and let's look at adding 2 vectors together. So if you're given the vector u and you're being asked to add it to, say, vector v, then you're being asked to add this vector with that one. Now, some of you have seen vectors, so you know how that's going to work, but let's look from the perspective of people who've never really dealt with vectors. You get to do a little bit of vectors, by the way, when you did trig right at the end. It's typically the last topic that you do, and it's also 2-dimensional when you do it. If you were going to invent a rule for adding 2 vectors, and you wanted a pretty intuitive, sensible rule, would it make sense that what you do is you add up the x's, the y's, and the z components together? Would that make sense? You want to add 2 vectors, you add the x's, so 1 and 0 gets me 1. You add the middle 2, and you get 3, and you add those guys, and you get 0. That makes life easy, doesn't it? Adding 2 vectors is really just adding the x's, adding the y's, and adding the z's, right? There's no real weird rule about it. Now, if you want to subtract 2 vectors, let's say v take away w, so you'd be taking the vector v, which is this guy, and subtracting the vector w, which would be that guy. And it shouldn't be a shock to you that basically, don't you take this guy, subtract that guy. X's, then y's, then z components. So you'd go 0, subtract 2, 1, subtract -1, and 3, subtract -1. And what you get is -2, 1 add 1 is 2, and 3 add 1 is 4. And that's how you subtract 2 vectors. Cool?
Is it supposed to be w minus w?
No. V minus W. What's this guy? I want to find the negative of the vector W. Well, here's the vector W. I want to find the negative of it. What would that, how would we do that? What would it be?
You distributed the -1 across each coordinate or each vector.
Each component, yeah. Agreed? Let's show you visually what these kind of calculations actually look like. So I want you to pretend that this is the vector u. And this guy here is the vector w. If you add 2 vectors together, essentially what you do is you take the vector u and you draw it first. And then wherever the vector finishes, you draw this guy. So can you imagine this one is W. If you then join the start to the finish, that last one, the one in purple pen, that's what U plus W looks like. Sometimes called the triangle of forces. Do you see how they work geometrically? You want to add two vectors together, you just place the first one, then join the second one onto the end, start to finish. That's what U plus V, or whatever the vectors are called, is equal to.
So could it almost be like you have a car at a starting point, and when it gets to a stop sign, it has to make a turn, and then it
Yep.
turns a certain distance, and then whatever that total distance is, it would be in a straight line.
Yeah. You could think of aircraft, because aircraft can bend weirder, right? So the aircraft flies and then it does a very dangerous quick right-hand turn. This vector, wouldn't that represent the single flight path that would get you to the same point from start to finish? Now, if that guy here represents W, what do you think negative W would look like if you drew it? If that was W, what would negative W look like?
We go in the opposite direction.
Yes. And wouldn't it be parallel and the same length, but just going in the opposite direction? So when you stick a negative in front of a vector, isn't the only thing you really change is the way it points? Instead of pointing up the way, it points their main way, or vice versa. So putting a negative in front of a vector is simply just changing its direction. Everything else looks pretty much the same. The arrow just changes up to down, or vice versa. So if you wanted to do a visual representation of a subtraction, right, and let's say I want to draw a version of this, can we pretend that this is what V looks like? And I'm going to pick,
So quick question,
yes,
if you multiply or divide a vector, then it will go parallel,
yeah,
but it will just shift. And if you
it'll
add
go
or subtract-
parallel and it will get bigger or smaller.
oh, it'll get bigger and smaller.
Yeah,
Okay.
yeah.
So
So-
it won't shift though, right?
If you shift, you mean change its angle? No, it won't shift.
Okay, that's only if you add or subtract it.
Yes.
Okay.
So we're going to subtract these two vectors. Now that's the vector V, and I'm going to pretend that this is what the vector W looks like. Now, if you want to do this calculation, what we do is kind of slightly cheap. Subtracting two vectors is the same as adding the negative of that vector. Now, what would the negative of W look like? Well, it would look just like this guy, pointing that way. Vectors don't care where you draw them, right? They're actually independent of location. Vectors are just a movement in 2D space, or 3D space in this case. So V first would be this guy, so there's V. Negative W is this guy, so when you add it, you would point that way. That's what negative W looks like. And then you could join the start to the finish, and that's what V take away W looks like. Do you see, it's really just another different kind of triangle. So adding and subtracting vectors basically generate triangles of forces. Sticking a negative in front of it just changes its direction. Suppose I asked you to find 2U. Right, so the calculation is find the vector 2U. That's a scalar multiple. It'd be 2 times that vector. And so the vector 2U would be 2, 4, negative 6. And what would that look like? Well, if that was the vector U, the vector 2U would just be parallel to it, but twice as long. Any questions, or does that make sense? Any normal scalar multiple of a vector just gives you another vector, and in this case, twice as long as the original. Do another scalar multiple. Just writing this guy down so I don't screw him up. Right, there's the vector W. If I asked you to find 3W, it would just be 6, -3, -3, right? If you drew it, that might be W. And 3W would look like that. But what would -3W look like? Well, if you're doing the calculation, you just multiply all these by -3, and you get that. But what would -3W look like? If I drew it up here, what would it be? That's what 3W looks like, parallel to W, but 3 times as long. What would this vector, -3W, look like?
Say the same length, but the opposite direction.
Exactly. So if you want to visualize what these calculations are, can you see that you can get a good idea of triangular forces when you're adding and subtracting, and then thinking of things parallel but pointing in the same direction or not, depending on is the multiple positive or negative. Are we good? Now, the last thing you do is you put the whole package together. So you might have a vector A, 1, 3, 1, B, 0, 2, -2, and C, 1, 1, 3. If you were given this calculation to do, you should be able to do it by just applying the various rules that we've looked at and putting them together. So if I was being asked to do this calculation, I would say, okay, let's do 2A first. 2A means double these guys. So 2A would be 2, 6, 2. Add 3B would be treble this guy. So add 0, 6, -6. Take away 4C would be 4 times this guy. So take away 4, 4, 12. Are you comfortable? 2A, 3B, 4C, these two added, the last one subtracted. You could then combine them. This guy plus this guy, take away that guy. That's the X component. The Y component, 6, take away 6. Sorry, 6, add 6, take away 4, that's better. And lastly, 2, add, yikes, -6, take away 12. 2, add nothing, take away 4, gets you that guy. 6, add 6, take away 4, gets you that guy. 2, take away -6 is really just subtracting it, so it's -4, take away that guy is -16. So if your question was, calculate what this is equal to, there's your answer. Right? 2 lots of A plus 3 lots of B, take away 4 lots of C, and this is what you've got. What would you be asked to do if they wrote that down?
You get the magnitude of 2,
Find its-
-2, 8, -16.
Agreed. Wouldn't you just find the magnitude of this? So in this case, it would be 464, 256. So that's 324, I believe. Not a very pretty answer, but it's an answer. Any questions? Right, so if I give you 2 or 3 vectors, do you feel comfortable about finding A plus B, 2A minus 3B, magnitudes, all sorts of combinations like that, the algebra of vectors, essentially? Okay. Now, some homework questions, you're not given the information like this. A will be called an I plus a 3j plus a k. And B will be 0i, so you don't write anything down. You just say 2j, take away 2k. And C will be 1i plus 1j, add 3k. If you use the basis vectors, this and that are equivalent. You agree they're telling you the same thing in 2 different ways. But if you're using this notation, won't you have to write this down in a different format? Me personally, this is what I do. I don't like this notation. I just make too many mistakes. So when I see 3 vectors like that, I immediately convert them into this format. Do all the things that they want me to do. And it's only at the end, when I need to, do I rewrite it as ijk. So for instance, this is the answer we got. Won't that be negative 2i plus 8j, take away 16k? And since the magnitude is a number, it doesn't care if it came from an ijk or anything else. Isn't the answer still the square root of 324? And so I don't care. So me personally, that's how I kind of get around the ijk initiation, because I just don't like it. It's just me. And other people like this notation and don't like that one, in which case they do all their questions this way and then convert them back if they need to. And the typical rule, I think, for WebAssign is if you get the thing written as ijks, they want the answer that way. If they give you the question written this way, they want the answer this way, right? So you just be consistent, and that'll keep WebAssign happy. How are we doing? Okay. Any questions before I move on to the last thing in this section? Okay. Right. The last thing in this section is actually in the homework right at the start. I think it's the first three or four questions. And let's have a look at them then. It says, question 1, are the following quantities vectors or scalars? So to be a vector, you need a direction, right? You need to have a plus or a minus, or at least a direction associated to it. A theatre ticket is scalar because it only has magnitude. Right, a theatre ticket is $4 or $54, right? That's all you get out of that. The current in a river, that's a vector, because doesn't a current in a river have a magnitude and a direction? Couldn't you be going upstream 4 mile an hour or downstream 4 mile an hour? Couldn't the current be at 30 degrees north, right? Or 55 degrees south, right? Doesn't it have a direction to it, the current? That makes it a vector. Do you have a direction? Yes, you're a vector. Are you only a number? Then you're a scalar. The initial flight path from Houston to Dallas, vector or scalar?
I want to say, I now realize it's vector, but at first I thought it was scalar.
Because you're thinking an aircraft flies at 250 mile or 950 mile an hour, right?
Yeah.
Which is true, it does. But doesn't an aircraft also have a direction that it flies in? In this case, from Houston to Dallas.
I
So
was
do
thinking
you-
it went in a straight line.
Yes, but isn't that straight line got a direction?
Yes.
That's what makes it vector then.
Oh, okay.
So the population of the world, that should be an easy one. Vector or scalar?
Scalar.
Because the population, whatever it is today, I have no idea, 7 billion, right? That's just a number, right? Now you could say, well, the population's increasing, but that still doesn't make it have a direction, right? It's just getting bigger. Now, this question is very visual, and it asks you to name equal vectors in this parallelogram. So when you're a parallelogram or any shape, an equal vector just means you're the same direction and the same length as somebody else. So AB is going from here to here, right? AB. Who else does that same direction length thing?
DC.
I think I heard it. DC, great. That's it. Right. DA. Oh God, where's that? DA is going this away, right? D to A. Would you agree CB is doing the same thing? I know it's not a choice here, but why is BC not the right answer?
Because
Mhm.
because it's it would, if it was BC, it wouldn't be going in the right direction.
Right. It's got everything else correct, right? It's parallel, it's the right length, but isn't it pointing the wrong way, right? So if you want to be equal to vector, don't you have to have the same direction as well as all the other details? So it would have actually been nice if they put that as a choice so that you could maybe get it wrong and learn from it, but they didn't even give you that as a choice. Now they've got a vector DE, so here is this guy DE. Somebody in this picture is doing that same basic length and direction thing. And that's the choices down here. What would DE be?
EB.
I agree. Would you go from there to there? Isn't it the same as starting here and going there? Right, same length, same direction. We don't care that you're in different locations. Vectors don't care about starting points. Just that you're the same parallel, right? Going the same direction, same length. And there's other ones. Right, here's a different one. Now we're going to look at how do you combine vectors in a picture, because there's no numbers to work with here. If you think, the way to think of it is like a road journey. And A, B, C, and D are just towns that you might pass through. And the final vector basically represents the single journey that would get you the same effect as the ones you're doing. So if you went from A to B, and then from B to C, wouldn't that be the same as going A to C? Does that make sense? Now, if you click on this guy, you want to do capital AC, so you go to vectors, you pick that guy, and you put AC. Right? That's how you get AC with an arrow above it. Hopefully that's the right one. Now, if you did this one, would you agree that C to D, then D to B is the same thing as C, B? Agree? Now, if you notice something, without even seeing that picture, so I'm hiding it now, this journey, followed by that journey, finally followed by that journey, is the same as what?
DCAB.
Only two letters. You can only have a
Okay.
start letter and a finish letter.
D and B.
Because as far as vectors are concerned, aren't you really only interested in the start and finish location? So that would be the end of that one. Oh, now I'll let you figure that one out. It's a good one. The last question, and then we're moving on to our next section, is this one. And it's kind of a trick question, although it's not really. If A, B, and C are vectors of a some triangle, and you go A to B plus B to C plus C to A, what's that the same thing as? Where would you start? Where would you finish?
You finish back to the point where you started, so wouldn't that be a zero vector?
Exactly. So what you're meant to do here is not write A to A, which kind of is right, but only like 90% right. You're meant to do the zero vector. So there you go, zero vector. Just hit bold, put 0, and you got the zero vector. And that is the end of the intro to vectors section. We're now going to move to our second and final section for today. And that is this fella here, the dot product. This guy here. Before I get started, has anybody seen or heard of the dot product? Even if you can't quite remember what it's about, do you have like recollections of a thing called the dot product?
I believe so.
Natalie, would it maybe be in Triggs that you saw it, or did you see it somewhere else?
I think I just remember the name. It might have been Trig.
Okay. So we are going to be looking at this thing called the dot product. And let me start by imagining that I have two vectors, u, so this one here, v. If you draw two vectors emanating from the same point, very often one of the things that you are interested in finding is the angle between the two vectors. So theta is very often the Greek letter we use for that, represents the angle between two vectors. And one of the main jobs, the main uses of the dot product is that it will eventually allow us to calculate that angle. So we are going to find out how to calculate the dot product first. And then we're going to later on today use it to find the angle between two vectors. And we're talking about the angle between two vectors in 3D space, like these two pens. We're talking about that angle there. So imagine I have a vector u, and its components are u1, u2, and u3. Okay, there's my vectors. And I have a different vector called v, and I'm going to call it v1, comma, v2, comma, v3. I try and make my u's and v's as different looking as they can, because if I write them quickly, they start looking like each other, right? So if you're wondering why my u's are so square, I just want to make them different looking, right? Now, we have a thing called the dot product, and it's written down like that. And you read that out loud as u dot v, right? Or you could say the dot product of u and v, but u dot v is much easier to say. So u dot v, the dot product of u and v. And you do it by the following formula. u1 v1 plus u2 v2 plus u3 v3. And that is one of our two dot product formulas. So if you tell me who u and v are by giving me the components, I can calculate this thing called the dot product. And at this point in time, we're not really going to do anything with it except just calculate it, right? Later on, we'll use it for this, but right now we're just going to get good at doing it, right? So I could give you a vector u, and tell you it was 1, 3, -2. And I'll give you another vector v, and it's 5, 1, 4. And the question could quite simply just be, find the dot product. Now, based on my formula, don't you basically just multiply these, add, multiply these, add, multiply these? So you're going to go 1 times 5, add 3 times 1, add -2 times 4. And you get 5, add 3, take away 8, and this answer happens to be 0. So far, so good. Right. So if I give you 2 vectors and I say find the dot product, this is how you're going to do it. Two more vectors. Suppose I have A, -3, -1, 7, and B is 2, 0, 1. If you're asked to find the dot product, A dot B, it will be -3 times 2, add -1 times 0, add 7 times 1. And that will be -6 plus 0, add 7. And this time, the dot product is equal to 1. How are we doing with the dot product? Are you comfortable with how to calculate it using this formula? Right? Multiply the x's together, add, multiply the y components together, add, multiply the z components together. And in this case, the answer happens to be 0, just that's what it is. This case, it happens to be 1. Next time, it's 42 minus 50. Any number could happen. This just happens to be the numbers we got with this one. Any questions about calculating dot product? Right. Suppose we give you some weird vectors. A, B, 7. B, 2A, 3. If I asked you to calculate the dot product, you would just say A times B plus B times 2A plus 7 times 3. And now, even although most of them are not numbers, it doesn't mean I can't calculate it. That's just AB, that's just 2AB, and that's 21. And these two can be combined. So the answer to what is this particular vector's dot products is that guy. So you can find dot products when everybody's numbers. You can find dot products if nobody's a number, right? You can still calculate the dot product. Just means your answer is going to contain variables. Right, how are we doing, guys? Still good? Okay, thumbs up. Good sign. Now I said there's 2 ways to calculate a dot product. And this is the first one, right? Here is the second method for calculating the dot product of U and V. It's the magnitude of vector U times the magnitude of vector V times the cosine of the angle between them. So if you are given a question where the information is, they tell you these numbers, right? That guy, and that guy, then you can also get the value of the dot product. So imagine I have a vector And all I'm telling you about it is that the magnitude of u is the number 3, and that the magnitude of v is 4, and that the angle between the two vectors is 30 degrees. You can calculate the dot product from this information. The dot product is going to be 3, that guy, times 4, that guy, times the cosine of 30 degrees. And I don't think I got my calculator handy. I don't, that's fine. No. Does anyone know the exact value of the cosine of 30 degrees? Pre-calc 2, trig, unit circle. Guy that looks like this. 30 degrees is this fella, right? You have a coordinate here. This guy is a half. This guy is root 3 upon 2. Isn't the cosine the x coordinate of this point? Which makes this guy square root of 3 upon 2. So when you cancel and simplify, you get that. You do not get, I don't know what that is because I don't have my calculator, but you don't get 7.81234. We do not want to know decimal approximations. So you are going to have to find exact values, provided these angles are in the unit circle, right? So if they tell you the angle's 22.9 degrees, don't worry about it. Can't you just go to your calculator and tell me the answer's 1.234? Because it's bound to be a decimal, right? There's no way out of it. But if this angle is 60 degrees, 45 degrees, 135 degrees, right? Things that are in the unit circle, you are expected to get their exact values. So maybe you want to look up your unit circle in case, you know, the situation appears where you need that. Are you comfortable about this second formula that can be used to get the dot product? Let's try another one then. Suppose I have a vector A whose length is 4, a vector B whose length is 10, and the angle theta is 135 degrees. And we're being asked to find the dot product. So it's the magnitude of A, which is 4, times the magnitude of B, which is 10, times the cosine of 135 degrees. That guy is in the unit circle. So that's 40 times. 135 degrees is roughly about here. And this guy is negative root 2 over 2, positive root 2 over 2. The x coordinate of a point is what the cosine is equal to. So can you see in this case it's negative root 2 over 2. Which means this simplifies down to that guy. Are we good?
Do you want us to memorize the unit circle or can we just print it out?
You better just have it somewhere handy. I would prefer you to do it, but you don't. I would just say I would prefer you to do it, but you don't need to, I guess. It's just so much more convenient to be able to do it. But if nothing else, have it beside you so that when you come to these questions, you can read off the answer. And if you do enough of them, don't you start memorizing them because, oh yeah, I've seen that one before, it was root 2 over 2 or something. If the angle is not in the unit circle, then it's not a biggie, isn't it? Just grab your calculator and start hitting buttons because, you know, there's nothing you can do about it. So now we're coming to, how do we find the angle between two vectors? Up to this point, we've only been finding dot products for various reasons. So here goes. if this is the vector u, and this is the vector v, and the angle between them, theta, would be that angle there, then if you want to find this angle, you use this formula. It says the cosine of angle theta is the dot product of u and v divided by the magnitude of u times the magnitude of v. And what this formula here will allow you to do is eventually to get the size of angle theta. And I'm really annoyed at myself by not having my calculator. So hopefully somebody here has got a TI-84 because we'll need it in a few minutes. So these questions are all going to take the same format. You are going to be given the components for u and v. Right? You're just going to be told them. Right, so you're not going to be given magnitude of u directly, right? You're going to be told this is u, this is v, and you're going to plug all the bits and pieces that make this here. And then you're going to be able to say the cosine of theta equals this number, and from there you should be able to get the angle theta. So if I know these two, the first thing I'm going to do is find the magnitude of u. It's that guy squared plus that guy squared plus that guy squared, and it's the square root of 14. I'm also going to find the magnitude of v. That guy squared plus that guy squared plus that guy squared, and that ends up being the square root of 2. I'm also going to find the dot product using the components. So it's going to be 1 times -1 plus 3 times 1 plus 2 times 0. And that's -1, that's +3, that's 2. 2 add nothing is still 2. So I am going to find these guys first. Once I know these guys, I can then use this formula, and it'll go something like this. The cosine of theta is the dot product divided by the two magnitudes multiplied together. That guy is 2. That guy is the square root of 14, and that guy times the square root of 2. So the cosine of the angle between the two vectors theta is this guy. So to find theta, you find the inverse cosine of this guy. Right, this is where I need the TI-84 guy. One of you please have a TI-84, otherwise this is as good as this question's going to get. Make sure that you're in degrees, because that's typically the way we'll do these, and find the inverse cosine of this horrible calculation. Now, when you're typing it into your calculator, it's the inverse cosine button. You typically get a bracket for nothing. 2 divided by, put another bracket in it, or you'll get into trouble. And then enter. So inverse cosine, brackets, 2 divided by, bracket, square root of 14 times square root of 2, close bracket, hit enter. Oh good, Calvin, looks like you're doing it for me. What is that missing angle?
It is 67.7923.
Okay, how about 67.8 then to 1 decimal place? Sounds good? I think you said 7.9.
You wrote 66, it's 67.
Oh.
67 point, yeah, 67.8's right, yep.
Yep, 67.8 it is to 1 decimal place. So if you did this vector in 3D space, right, might be that pen there. And if you did the other vector in 3D space, it might be this red pen here. The angle between those two pens would be 67.8 degrees. That's pretty amazing that you can now find the angle between two vectors in 3 dimensions using this formula. Looking good? Try another one. Let's call it A. And it's 3i plus 2j minus a k. And B is an I plus a j plus a k. Now, though I don't like that notation, you are going to see homework questions with it. So, let's deal with it. This is how I deal with it. I deal with it by avoiding it. Now, since this question is going to be find the angle theta, right? Find the angle between the two vectors. Would you agree it doesn't really matter if I stick to this notation or that notation? This notation to me is just easier to handle. That's why I pick it. So we need to know the magnitude of A. We'll get that in a minute. The magnitude of B. That'll happen after that. And the number, the value of A dot B. Right, magnitude. 3 squared, 2 squared, -1 squared, square root of 12. Magnitude of B. 1 squared, 1 squared, and 1 squared. Magnitude of 3. A dot B. 3 times 1 plus 2 times 1 plus -1 times 1. And that gets me 3, 4, 5. That gets me 4. And I have everybody I need now. Write down this formula. The cosine of the angle between them, theta.
So for the magnitude of A, wouldn't that middle one be 4?
Thank you. Well got. Caught just in time, actually. A dot B over magnitude of A, magnitude of B. So it's going to be 4 square root of 14 and square root of 3. And basically, we're on to calculator. The angle will be the inverse cosine of that guy. And on your calculator, can't emphasize this enough because it's so easy to screw it up. Inverse cosine button, the bracket that you tend to get for free. 4 divided by a bracket, square root of 14 times square root of 3, close bracket, and finish with press enter. Going to put you in the spot again if you've managed to do it, Calvin. What does this one look like?
51.88, so 51.9.
We feel comfortable with that? 51.9 degrees. So far, so good. Right. Put you on some puzzle stories. I have two vectors, A and B. I'm not going to tell you their values, I'm not going to tell you their magnitude, I'm going to tell you nothing except one thing. The dot product is 0. I can now tell you what the angle between the two vectors is, based only on the fact that the dot product is 0. Don't know anything else. What's the angle between the two vectors when this happens?
90 degrees.
It is. You want to share with everyone how you figured that out?
Because the cosine of the angle is got 0 on the top of and not 0 on the bottom. So you just know that that's equal to 0. So the inverse cosine of 0 is 90 degrees.
Nailed it. You agree? That makes sense? And that is a property. And the property says if a dot product is 0, the angle is 90 degrees, right? Or if you want to, I guess, pi over 2 radians, I guess you could have radians, right? It's the same thing, right? You will see a word that you might have met before. If two vectors are orthogonal, it just means that the angle between them is 90 degrees, right? So if they say to you, prove that these two vectors are orthogonal, what they're really saying is prove to me that the angle is 90 degrees, right? And the simple test for that is actually that guy, right? Just find the dot product. If the dot product is 0, they're orthogonal, right? The angle is 90 degrees. If the dot product is any other number, it's not going to be orthogonal. Now, what does orthogonal look like? Can you imagine that's A and this is B? Orthogonal just means that angle there is 90 degrees. And now in 3D world, can't 90 degrees be sticking up in the air like this? Right? That's 90 degrees, right? In fact, isn't that 90 degrees, right? And this is 90 degrees, right? Orientation doesn't care, right? It's just how do they two interact with each other, right? It doesn't need to be horizontal meets vertical, right? Can't it be like this? Still 90. Oops, still 90. Good. Now, suppose I have two vectors. Oops, try it again. And this vector is 1, 3, -2. And this vector is 2, 6, -4. And the question is a yes/no question. Are the vectors A and B parallel? So yes/no questions are dead easy to do, because don't you just say yes, and if it's not correct, you then go back and say no. But we're not going to do it that way, right? We're going to have to figure a better way of deciding are two vectors parallel. And we're going to do it by finding the angle theta between the two vectors, right? Now, parallel doesn't care which direction that you're going. So what do I mean by that? Two vectors going the same way are parallel. Even if one's longer than the other, they're still parallel. Two vectors going opposite directions, but can still be parallel, right? So here's the question. What angles, and there's two of them, do you need to get to prove that these two are in fact parallel? So what should be the angle between two vectors that are parallel? So here's my two vectors. What angle should there be when you nose to tail them?
So I'm guessing here, but I'll say 180 degrees, maybe?
Yep. And that would happen when the pens look like that. And that's correct. What's the other possibility, which also means that they're parallel?
Guessing 0.
As in 0. So if you can find the angle between two vectors, and the answer isn't 90 degrees, because that makes them orthogonal, but the answer ends up being 0 and or 180, one of them or other will happen, depends on the context, you can say for certain that they are parallel. So I've said these are parallel. Let's take it through the process to convince us that it is. Vector A is the square root of 1 times 3, that guy, so it's 1. That guy 3 times 3, that's 9, and that's 4. So that makes that the square root of 14. The magnitude of B is that guy is 4, that guy is 36, and that guy is what, 16. And I believe that's the square root of 56.
What's the 1 plus 9 plus what's that number?
That's a 4.
Okay.
And the dot product, because we need that, it's going to be 1 times 2, add 3 times 6, add -2 times -4. God, that's a hard one. Here we go. 2, add 18, add 8. That wasn't that hard. It's 28. Okay. So we're going to use these 3 numbers to find the angle theta. And it better be one of these two, because I've told you that these guys are parallel. So let's see if I'm right. The cosine of theta is the dot product divided by the 2 magnitudes multiplied together. The dot product is 28. That guy is 14. The other guy is a square root of 56. And so theta should be the inverse cosine of all that.
It's 0.
Oh, John, you did it in the TI-84 or whatever. You got a 0. And isn't that what I said? 0 or 180, right? Both mean they're parallel, just parallel in different ways. Now, if you're not orthogonal and you're not parallel, then you just belong to everybody else, right? The others, right? So sometimes you get a question where they give you 2 vectors and they give you a choice. They say to you, is it orthogonal? Is it parallel? Or is it just something else, right? That kind of choice. Aren't you going to find the angle between them in each case? And if the angle's 90, orthogonal. If the angle is 0 or 180, in this case it's 0, parallel. And if it's 42.1 degrees or whatever it ends up being, isn't that simply just going to be as one of the others? Are we cool with that? So dot products are very powerful at doing one particular job really well. And that job is, oops, Cengage just disappeared on me and I was about to, okay. I'm going to have to go back in. I was about to show you, damn thing logged out on me, some of those homework questions. So if you could just bear with me for a few minutes while I think it must have timed out while we were doing all this good stuff. So give me a few minutes. That's good. That should be good. Almost back to where I should be. And that goes over here. Let's do a view. Looks good. Right, I'm almost ready. Let me find one of those questions. Right, ready now. So, as an example of some of the things that we've been doing, question 7 is simply, here is 2 vectors A and B, and it gives you a funny little thing. One says exact and the other says approximate, right? The approximate ones, do you know those questions where it was 65.9 degrees? That kind of question? Then you type in 65.9 degrees. Now, to get that, didn't we do an inverse cosine of something divided by 2 other guys? That's what they mean by the exact. Now, if you're trying to get the inverse cosine, you need to go over to the trig button. And you see the inverse cosine button. Don't try and type it in through the keyboard. It might look exactly like what's in front of this screen, but WebAssign will just turn around and say, I don't know what you're talking about, right? So you have to hit the trig button and pick inverse cosine. So let's just say that the dot product was 42, right? And it was divided by the square root of, let's pretend we know, the square root of 12 times the square root of 32, right? That might be the calculation that we use to get it. I'm just kind of randomly picking one, but do you get what I'm getting at? WebAssign wants it in a very specific way. So that's what it means by exact value. And that's what we got from the calculator, right? In this question here, do you see they just want to know the answer? So it might well be, 65.9 again, and we don't need to worry about exact value, right? And if you look really carefully, do you see they're telling you they want the answer as degrees, not radians, which is typical. Right. And this one here is actually a video and an example of doing everything that we did. Right? It's just a little take you through the steps, right? And that's fine. And they just wanted the answer in radians because they felt like it. Here's another question. Again, it's going to use finding angles. Here we have 3 points on a triangle, and it's saying, is this triangle right angled? And you're going to use vectors to make up your mind, right? You're going to do vectors. So let me leave that guy and show you not the answer, but how you would get the answer, right?
So this may be a silly question, but
Yeah.
is the radians like in the unit circle, for example, is one of them square root of 3/2? Those are considered
Well,
radians.
one of the angles is square root of 3 upon 2. That would be pi upon 6, for instance. No, when they're talking about radians, they just want the answer to be, make sure your calculator's in radians. And instead of getting 57.1 degree, you might get 1.2 radians, right? That's really all they mean.
Oh,
In those questions, it's not really a unit circle question. It's just a round off to nearest number kind of question.
okay.
Most of the time they want degrees, but if they say radians, do the exact same calculation. Just make sure your calculator is in radian mode, not degree mode. That's probably all you need to worry about.
Okay.
Now, so imagine that that's P, that's Q, and that's R, right? And I'll make no attempt to be accurate, right? You're told the coordinates are P, Q, and R, right? In this question. And we're being asked, is it right angled or not? Now, couldn't you just say yes, and if you got it right, you were right, and if you got it wrong, you just say no? But we want to learn how to do this. So here is a strategy for finding out, is this right angled or not? First thing I would do is find these 3 vectors. I'd find PQ, I'd find PR, and I'd find QR, right? There's my vectors. Now, if I only use these 2, shouldn't I be able to find that angle there? And if I use the 2 that go here, couldn't I find that angle there? And if I do these 2, couldn't I find that angle there? So basically, couldn't I find the size of all 3 angles in that triangle just by picking these fellas, right? Any 2 of the 3. For instance, wouldn't these 2 tell me the size of the angle P, right? PQPR. If any of my answers, as I pick them, end up being 90 degrees, don't I stop right there? In fact, if my dot product is 0, don't even bother doing the rest. If the dot product is 0, doesn't that mean it's 90? I stop there. If none of them are 0, doesn't that mean it ain't right angled? Right. So find the missing angles, or just stop at finding the dot product, right? If the dot product's not 0, you know you're not going to get 90 degrees, right? So you can move on to find the angle Q, and if that doesn't work, you can move on to find the angle R. I happen to know the answer to this one is that it is going to be right angled, but you still have to figure out which one it is. It might be P, it might be Q, or it might be R, but one of them does work. That makes sense? Right, now, back to the homework. This is question 11 we're talking about now. Here are two vectors. Are they orthogonal? Are they parallel? Or nothing special? Haven't we talked about that before? Right, this is a classic, find the angle between A and B. If it's 90 degrees, it's orthogonal. If it's 0 or 180, isn't it parallel? And if nothing happens, right, if it's just 42.1 degrees, it counts as an either. And don't you do it with that guy, and you do it with that guy. And there's a little red herring in here. I couldn't avoid it. That's, I think, the only time I let a two-dimensional slip by. These two vectors are only two-dimensional, right? They've only got two numbers in them. But you can still do the dot product, and you can still do the magnitude. So do the exact same thing, but you only do it with two numbers instead of three. And if the angle's 90, it's orthogonal. If the angle's 0 or 180, right, they're parallel. And if it's none of those, it's neither. Are we good on that? Right. If you get the IJK guys, my advice is turn them into these guys and do the question. But if you're comfortable with IJKs, I don't mind, right? Do it that way. This is question 12. Let me zoom out of here. This is going to be the last question with dot products, not the last question for today. Still have some things to go over, but for dot products it is. Here are two vectors. I'm just going to call this guy A. No, I won't. I'll call it U. And it's -10, B, and 6. And the other vector, I'm going to call it V, even though it doesn't have a name. And it's B, B squared, B. And we are being asked this question. For what values of B is or are these vectors orthogonal? So I'm going to use the shortcut. If you are orthogonal, what number will the dot product be? If U and V are orthogonal, what number will the dot product be? Big zero? Agreed? Dot product? 0. Right, let's do the dot product. The first vector is that guy. Dot product. The second vector is that guy. And the answer needs to be 0. This guy times this guy, so it's -10 times B plus B times B squared plus 6 times B is equal to 0. So that's -10B plus B cubed plus 6B has to be 0. All I'm going to do is combine like terms. And now we need to solve this equation, and all the solutions, all the values of B that come out of this is what we're after. Any ideas of how to tackle this question? I want to solve this equation.
Can't see the other side. You probably would take a B out of the left side.
Okay, so take out a common factor of B. Good start.
Then
Anything else you can do?
divide that the whole thing by B.
No, don't go there, John. I like this
Okay.
bit. The good start. And the problem with dividing by B is you'll lose one of your solutions, and I don't want to do that. I want to keep them.
Okay.
But is there anything you can do with B squared minus 4? Is there a way you can factor that?
Break it apart.
Okay. What two numbers should fit here and here to factor that in? It's called the difference of two squares. That's the name we give to this particular situation.
+2 and -2.
Which means there are now three solutions, and that's you finished. And what are the three solutions? B could be 0, right? I didn't want to lose that one. That's a possible answer. B could be -2. And lastly, B could equal 2. And if you took that value, say 0, and put it in here, you would get two vectors that are orthogonal. If you replace the B with -2, you would get two vectors, different, but still orthogonal to each other. And then if you did 2, you'd get two vectors, again orthogonal. So we solved the problem. These are the only values of B that make these two vectors at right angles orthogonal to each other. Next thing, actually the second last thing for today, is called direction cosines. There are a couple of questions in the homework asking you to find these things called the direction cosines. So I'm going to try my best late on in the day when my brain's not functioning even vaguely well. I want you to imagine that you put a vector right at the origin, and this is the vector, and I'm going to call it V. Now here is the x-axis, here is the y-axis, and here is the z-axis. So far, so good. Now, every vector that is centered at the origin makes angles with the x, y, and z axes. For instance, the angle this vector makes with the x-axis would be this angle here. That makes sense? So there's my x-axis. This is my V. Can you see the angle? It's about here, roughly, right? Now, it also makes an angle with the y-axis, which would be this angle here. And it makes an angle with the z-axis. It would be that angle there. Would you agree typically those three angles are different from each other? There's no reason they should be equal, right? The angle you make with the x-axis has really got not a lot to do with what you do with the other two. Now, we have names for each one of those different angles. The angle the vector V makes with the x-axis is called alpha. The angle that it makes with the y-axis is called beta. And the angle that it makes with the z-axis is called gamma. Now, you notice gamma looks like alpha turned on its side. Alpha, beta, and gamma. These angles are your direction cosines. It's a funny name for them, but you'll see in a minute why they're called that funny name. The angle that a vector makes when you place it starting at the origin, the angle it makes with the x, the y, and the z axes are called the direction cosines. Okay, that's their name. So how do you calculate them, right? How do you find out, is that 82 degrees, that's 90, and the other one's 44, right? That kind of thing, right? Here is your formula. The cosine of alpha is equal, oh, first I've got to tell you who V is. V is V1, V2, V3, right? I'm just giving you a generic version, right? Cosine of alpha is V1 over the magnitude of V. Now notice V1 doesn't have any arrow above it, because isn't V1 just a scalar, right? It's just the x component, it's a single number. Now, the cosine of beta is V2 over the magnitude of V, and the cosine of gamma is V3 over the magnitude of V. Can you see why these angles are kind of called direction cosines? Now, if you want to find, as you do alpha, then beta, then gamma, don't you have to take the inverse cosine of that guy? For this one, the inverse cosine of that one. And lastly, for this one, the inverse cosine of that guy. How are we doing? You still with me on this? Right. So let's put a number to it. Let's write down a vector v and find the direction cosines, then find the angles themselves, right? So the vector v is going to be 1, 2, -2. The magnitude of v then is going to be the square root of 1 squared plus 2 squared plus -2 squared, which is the square root of 9, which is the whole number 3. So I deliberately picked a nice number. The cosine of alpha then is v1, which is this guy, divided by the magnitude. It's a third. The cosine of beta is 2 thirds. The cosine of gamma is -2 thirds. Are you comfortable about how to get the direction cosines, the alpha, beta, gamma guys, right? V1 over the magnitude, the value of V2, which is this one, over the magnitude, and then V3 over the magnitude. Now, to get alpha, you find the inverse cosine of a third. To get the angle beta, you find the inverse cosine of 2 thirds. And to get gamma, you find the inverse cosine of -2 thirds. And this is where I kind of need help again. Let's do it to, I don't know, let's do it to 1 decimal place again. Inverse cosine of 1/3 in degrees to 1 decimal place.
Okay, so the first one is 70.528 or 70.3.
7.5?
Yeah.
That do? Okay.
And then the next one is 48.2. And the last one
Should be
is-
over 90 anyway.
the last one is 131.8.
If you look at those 3 angles, do you know they don't add up to 180 in case you were hoping some nice pattern like that was happening? Do you notice they just add up to some random number that's not very interesting? So direction cosines are, for the most part, couldn't they all be quite big, all be quite small? They could all add up to 80, they could all add up to 180, right? There's any number, any combination. So there's nothing really to plan there. You just go with the flow and the angles you get are going to be hopefully correct. Are we comfortable about how to find direction cosines and then the missing angles? Do you want to see another one, or is that one a good template for the 2 that you're going to do? We get a thumbs up, I'll go for that. Now, here's a useless piece of information, but it's kind of cool. I'm going to do a unit vector. If I wanted to find the unit vector of this guy, right? I could go through the entire performance, but you don't need to. The unit vector is the vector made up of the direction cosines. Is that not fun? When you found the unit vector, remember finding the unit vector earlier today, right? Those numbers are actually the direction cosines. Now that's a relationship you might not have expected, right? The angles have no relationship, right? They can be anything, right? There's nothing going on there. But these 3 guys, when you put them into a vector, is the unit vector of the original. I think that is kind of interesting. So I got a couple of thumbs up on that, which I'm pleased for. Hopefully that makes sense to the others. I'm going to start one last question, because it is a direction cosine question, and after I just looked at it, I realized I had something that we haven't covered. What do you do if the vector that they give you, that they want you to find the direction cosines for, doesn't have numbers? Is it even possible to calculate the angles in the direction cosine? And the answer is, surprisingly enough, yes. I can actually get numbers for some of these results. Let's see if I can do it. The magnitude of V is going to be the square root of these guys, right? C squared plus C squared plus C squared. And isn't that going to be the square root of 3C squared? Are you with me? Wait a minute. Can I not simplify that down as the square root of 3C? Can't you separate out the square root of C squared and just get a C without a square root? So the cosine of alpha is C over the square root of 3C, which cancels down to 1 over root 3. And the cosine of beta and the cosine of gamma, it won't surprise you. Can I just cut corners and tell you that aren't all of those going to also be 1 over root 3? So those are numbers, aren't they? There isn't any C's. And if you know these guys, I'm not going to do it, but can't you just find the angles alpha, beta, and gamma now? I don't know what the inverse cosine of 1 over root 3 is, but whatever it is, it goes there, there, and there. So that's how you would finish that question. Okay, and our last thing for today, and that'll get you covered for your homework, is a concept called work done. So imagine that you have it's typically a box on a hill. They like boxes on a hill for whatever reason, right? And you are taking this box and it's starting off, let's say the coordinates of this point are 0, 6, 8. And it's going to finish here on the hill, and it's going to finish at a point called 6, 14, 24. I'm basically doing a version of question 15, which is the only one that does this. And you are pulling it up a hill, and the force that you're pulling it up with, let's put it there, and we're going to call that vector V, and it's going to be 8, negative 6, 9. Now, if you're pulling something up a hill isn't the most efficient one, pull at the same angle as the hill. But this guy is not very efficient, so do you see I've deliberately made the angle a little bit different from the slope of the hill. We're being asked to calculate the work done. Now, the work done is a number. I believe the units are joules, right? So you talk about 40 joules of work, right? Or 4,000 joules of work, right? And I'm going to call this guy A, and I'm going to call this guy B. The formula for getting the work done is the dot product of A dot B V. So AB is where you start and where you finish, and V is the force vector. Now I know who the force vector is. It's over here. It's 8, negative 6, and 9. And isn't the vector AB just the vector joining A to B? So let's see if I can do that in my head. 6 take away nothing is 6. 14 take away 6 is 8. And 24 take away 8 is 16. So the work done is going to be 6 times 8, add 8 times negative 6, add 16 times 9. So that's 48. Oh, that was nice. Take away 48 plus 90 and 54, which is add 144. And so I believe the answer is 144 in the units of joules. So if you've got a box and you're pulling up a hill and you know where it starts and you know where it finishes, right, by coordinates, and you know the force vector, I'm calling it V, but maybe next time they'll call it F, whatever letter of the alphabet they decide. This is your force vector, the way you're pulling it up that hill. The work done is the dot product of the position start to finish, AB, with the force vector. Right, for the physics guys amongst you, you could get work done equals 0. How could that happen? Well, could you imagine that the energy that you use to pull it up the hill, you get it back as kinetic energy when it falls down the other side or something? So I guess it could be 0, right? Can you get negative energy if you do a work done situation? Is it possible to get energy out of something rather than having to put it in?
Well,
Is that
the friction could cause heat, I guess.
right? So you could get heat energy out of it. So it's okay for this work done to be 0 or negative. The most likely situation, isn't it, is going to be a positive number, because almost everything that you pull uphill is going to cost you more than you get, right? Sometimes you get energy because don't you get potential energy for pushing up the hill, so it's now got more potential energy than it used to have, right? And you might get some friction out of it, so you might get some heat energy out of it as well. But the chances are you're going to put more energy into it than you're going to get out. So in that case, it's a positive number because work done is the amount you used to get the job done.
So suppose you pulled the thing up the hill
Mm-hmm.
and then you let it go and it slipped past the point that it was lying originally.
You could theoretically get more energy out of it than you used.
But does that, just because it went past the original point, does that make it negative? No, right?
I'm not into physics. I don't know. Does it? I guess it depends, right? It depends on how you want to describe the start and finish states, right? Yeah. I don't know. I'm not going to go there. I'd probably tell you a made up answer that was wrong. It might well be that that could be a case. Right? But normally in physics, don't they tell you lots of lies, like it's frictionless, right? Isn't that a big lie? I mean, have you ever pulled anything up a hill and there was no friction, right? And there's no inertia, right? In other words, when you start pulling it, it's ready to move, right? You don't have to give it a little tug to get it going, right? All sorts of things that we ignore because it simplifies the math. So I think we probably simplified it to death in this question, but it gives you an idea that it's a sort of a way to deal with it. And although we are finished, and we are, I want to show you one little thing in the homework, and that is the last question, which is question 16. And question 16, you're going to have to watch the video, and it'll take you through the process of calculating a thing called the scalar projection of a vector and a vector projection of a vector. And it's kind of interesting, but I don't want to do it. I want you to learn this yourself. This is actually used, because I know, because I had a student once who was really into computer graphics and animation, and he says that they use projections of vectors in animations. So you've got an object in 3D space, at least you've got a model for it in your computer, and then you might want to make a shadow of it. But wouldn't the shadow be the projection of that thing onto the floor, for instance? Or maybe a shadow on a wall, wouldn't that be a projection from the light source to the object to the wall? So these things called projections are sometimes used by people in animation, which I thought was kind of cool. But that is it. Anything else to say? Thank you for turning up. I know it's a lot of time listening to me, but hopefully you've got some benefit out of it. You'll be ready for your homework.
Thank you.
On Friday, probably late in Friday, more like 3, 4 in the afternoon. the online test one will be available. When you do want to do that test, you've got 2 hours to do it. Should only take 90 minutes. I've mentioned that before. But please don't click on it out of curiosity. If you click on it, the counter starts. And you can't just go back out and say, oh, well, the counter will freeze. No, the minute you enter it, you got to do it in the 2 hours. So don't touch it until you're ready to do it. That's my advice. Homework's fine. Can't you go in and out of homework as many times as you like? Nobody cares. But the online test, the minute you click on it, that's it. You got to do it. So when you're ready for it, great, but don't do it until then. And I'm going to hang about for any homework questions. Otherwise, bye-bye, guys, and thank you again.
So I do have one homework question.
Sure, which one is it?
It's for 12.1
Okay,
question. Oh, I just had it.
okay, I'm looking at it as we speak. So 12.1, let me get yours, Calvin, because I can look at your specific numbers.
Okay.
So,
Oh, it's question 8.
question 8, let's get D.
'Cause I think what's happening is that I'm not entering it in correctly.
Okay,
Okay,
Correct.
so I did get so I know it's not 8. I did get 82 for an answer. I
Good.
just was not sure about putting in I misread it as saying find an equation. I thought it just wanted the answer.
Okay, so do you have any more guesses left?
Yeah, I think I still have a couple.
Okay, so let me go through with your 82, which I like, because 82 is actually part of the answer and is the correct, right?
Okay.
In this question, you're told the center of the circle was 5, 6, 3, and you found the radius, which was the square of 82, and then when you square the radius, that's the 82. I'm suspecting that's what you did.
Yeah.
Right, what they want you to write down is x minus 5 squared plus y minus 6 squared plus z take away 3 squared equals 82. That's what they're after.
And it's for that point in the center.
And that these numbers come from the point in the center. Do you see how?
Yep.
They all happen to be negative, but that's only because these are all positive, right?
Yep.
So that's